We often say that of excellent reference is your textbook. So what we'll do in this series of videos is we'll go to the online version of your textbook and then go through the subject matter in such a way to perhaps point out the significant things and things you should know. Now, if you read the textbook directly and take notes on it, that would be a good pattern as well. But this is a backup and meant to be a reference. So this is the way it's set up. You'll have the topic. We skip chapter 1. We start with symbols and terminology, so we're going to be building vocabulary. Now here they give you the objectives of what we're going to be looking for. Use 3 methods to designate sets. Understand the important categories of numbers and determine cardinal numbers of sets. And there may be a few words there that you're not sure of yet, but we'll go over that. Distinguish between finite and infinite sets, and then determine whether 2 sets are equal. Now, this is the background you need to later do your study plan and then develop mastery of the vocabulary and topics and examples. So when you take your test, you'll be confident you're going to do well, because you've earned the right to do well by this mastery. So we're going to start off by, again, reading some of this, but not every single thing, and you could always pause the tape to read something in more detail. But we're going to look at this word first, a set. What is a set? Well, by definition, it is a collection of objects. And since this is a math course, it will be numbers. Although sometimes we use letters as well to indicate things. Now, the members of the set, that would be one way to describe those that are in a set, also referred to the elements of the sets. So the elements and members of the set are synonyms. Now there are 3 ways used to describe sets. One is a word description. Another is the listing method. And a third, the set builder notation. And there will be times when I write little notes for you out here. And if you are taking notes on this, which I think is a good idea, you'll have these additional references on the side. So, let's start off. The set of even counting numbers less than 10. Well, that's pretty general. That is a word description. Now, again, you may not know what counting numbers are, and I will be giving you some background on that as well. And here is our first side note. The first set of numbers are the counting or natural numbers. And what are they? Well, on a number line, and we'll be using this a lot in this section, our first number, if we were going to count something, would be 1. So we'd put like a little dot at 1. This would be the graph of 1 on a number line. Then 2, 3, 4, 5, 6. And then to indicate that this pattern continued, we would make our arrow here darker. That pattern continues. Another way to show that the pattern is continuing is we put 3 dots there, which is the ellipsis, which indicates that this pattern continues. As we'll see shortly, they use this ellipsis a lot. So our first set of numbers are the counting or natural numbers, and that's what we see here. So we've defined what counting numbers are. So when they're talking the set of even counting numbers, as you look here, which would be the even ones? Well, 2, 4, 6, and it has to be less than 10, so we would add the 8 when we are actually listing the elements of our set, which are described there in words. This would be the use of brackets, or I should say braces, in this case, the listing methods. Now the set builder notation has a way of being set up, and let me just mention it here. You have a brace. You're describing members that are X in a sense, and then you put a vertical line and say X is such that, and then you give a description of it, and then you end with a brace. So again, they're showing here X is such that X is an even counting number less than 10. And you might say these first and third methods are very similar, but here it's just English. Here we're starting to use symbols and tying it into a mathematical notation. They're describing here that X is often the common choice to represent something. And that's what algebra is all about, the use of letters to represent things. In using the textbook, we often have these little anecdotes where the basic idea of set theory were developed by, I believe that's George Cantor, and you can read a little bit of that. So let's continue then. We often say that sets are commonly given names, usually capital letters, such as E for the set of all letters of the English alphabet. So you're defining this as E is the set, capital letter E, and then you're actually listing all the letters of the English alphabet. Now, there is a shortened way to write this. Instead of having to write them all, when we set up a pattern, as we see here, A, B, C, D, and then as it finishes, X, Y, Z, and then to indicate that this pattern continues, we're using commas to separate the members or elements of the set, and then we're using the 3 dots, which is the ellipsis. And there's the word ellipsis right there. And you would want to put that in your notes. And once again, the definition of an ellipsis is that it indicates that the pattern that it follows or precedes is the same pattern. Later in the text or in our course, we'll be thinking what would come next if you didn't know, by developing what is the pattern? Or it could even be this way. You've put just the last letter. That pattern will be continued. Some more vocabulary. Every once in a while you'll find that a set may be defined that there are no elements in it. So you might say, if your statement was the 6th Saturday in every month, and you might say there could be 5 Saturdays maybe, but there's never a 6th Saturday in a month. So this would be a set that is an empty set. Or another way of describing an empty set, a null set, and a symbol to indicate that would be a circle, which is like a 0 with a slash through it. That's to denote it. Or, as they're illustrating here, braces with nothing in it. Now, they are cautioning you here that if you were to say, well, that's an empty set, and this is an empty set, so I will put them together. No, because here you're saying the element is an empty set. So they're describing that right here, that you cannot do it this way. It's either the empty set solution, symbol, or the bracket, the braces, without an item in there. Not this. All right, let's go on to our next. Now the text has given us some background. Then there will be a series of examples supporting what we've just discussed. So here are the questions A, B, and C, and they are followed by the solutions. So as you do your practice and your quiz-mes to earn mastery, they will be giving you specific questions like this, and then you are to provide the answers. So I'm not going to read every example for you, but looking at what they've done, here this is the words describing the elements of a set, and here you list them. Then they're asking you to list all of the elements, doing away with the ellipsis, and that's what they do here. And then this one's interesting. Here they're showing you in set builder notation is the counting numbers between 4 and 5. Well, there are no counting numbers there. So this is an empty set. Now as we continue with the text, it says, for a set to be useful, it must be well defined. And for instance, if we have the set of all letters, we know that Q is in that set of our alphabet. So we would describe that as saying Q is an element. We're using this symbol here, which we see down there, is an element of E. So you are defining that. Now, in the Greek alphabet, there is a letter theta that looks like this that is not an element of set E. So you would say theta is not an element of set E. Remember, set E we defined as the English alphabet. And the use of a slash through the symbol often is used as making it a not true thing. Another example of this is we have an equal sign, and then we put a slash through that, indicating it is not equal. Now, looking at some other material here, it's talking about a singer. Suppose letter C, capital C, is the set of all good singers. Well, here, this person may or may not belong to that group. How would you rate good? How good is good? So I recall one time I talked to a student, I was saying Frank Sinatra. And some people may not even know who he is today. Well, to me, he was a great singer. But I talked to someone and they said they didn't think he was that great. So how good is good? Well, if you define that a particular singer is an element of the set, then by that definition, it becomes a member of that set. So, again, sets are useful as long as they are well defined. And you'll get a chance to work on some examples now. So here we are asked to apply the symbol is a member of or is an element of. And we're deciding whether the statements are true or false. So here we're saying 4 is an element of this set. Do we see a 4 in there? No. So the statement is false. 0 is an element of this set, and 0 is present. So that is true. Now, 1/5, now note the sign here, that is read is not an element of this set. And it's not found there, so that is true. And you might say, well, this is not too difficult as long as you know the vocabulary and the symbols and you're thinking about them. Now, I introduced a little background earlier. Now they're going to introduce the set of numbers more formally here, and we'll look at the topic cardinality. Well, we're going to use a number line to illustrate what they have here, but these are the sets of numbers in what we call the real number system. And these are the numbers we particularly include in our textbook here. And the reason we're using this, and you need to be familiar with it because we often, this is what we use for our examples. So the set we've defined so far, and I'll put it up here, were the natural or counting numbers, which we defined as 1, 2, 3, and then following that pattern, or using an ellipsis, this would go on to what we call infinity out here. So these are the counting or natural numbers. Now the next set they're going to introduce are the whole numbers. And if you look at the way they are listing them, we just add a 0. That makes the whole numbers. Just adding a 0 to the counting numbers. So now we have two sets, and we've made a graph of them. And this is just the roster notation, as it's sometimes called, where we list the elements. Now, integers are our third set. Integers are the opposite of our whole numbers. That is, if we have a 1, what do we need to add to a 1 to make it a 0? And the answer is its opposite, or a negative 1. So when we have whole numbers and their opposites, and this goes off to what is called negative infinity out here, then we have what are called the integers. And we would write it in roster notation by, again, the ellipsis. It's coming from negative infinity and then goes up to positive infinity following this pattern. We then get into the next group, which are referred to as the rational numbers. And I often like to refer to them as, if we were on the number line, there is a number right there. And what is that number? Well, I was hoping, and I may not have it exact, but it's 1/2. Now, if I went, and let's change colors here, I went right about there, and let me write these over here. That one is going to be 1/3, kind of running out of room. So anyway, I have two fractions, a 1/2 and a 1/3. And if we were to convert 1/2 to a decimal fraction, that would be 0.5. And if we converted 1/3 to a decimal fraction, that would be 0.3. And the 3's would repeat. And the pattern, the repeating pattern, we usually indicate with a repeating bar over the 3, because that's the part that repeats. Well, if we have a fraction between our integers, then along with the integers themselves, we now introduce our next group of numbers, which are the rational numbers. Now, what's happening to our decimal here? Well, we say it terminates. It's 5 and that's it. What happens to our decimal here? Well, it's 0.3 and it repeats. It's the same 3 repeating. Well, there are a group of numbers, which is about here, which is the square root of 2. Now, the square root of 2 is on the number line, but when we convert the square root of 2 to its decimal form, it's 1 point, and I went to my calculator, plug that in, and it's 1.41421356 and that's where the calculator ended, but it continues to go on, and we describe that as non-terminating. It doesn't terminate. So we call those that in their decimal fraction form that do not terminate, repeat, but do not terminate, we call those the irrational numbers. Now, the irrational numbers then, and the rational numbers. Now remember, all these integers, all these whole numbers, natural numbers, they're all rational numbers as well. It's only the irrational that are in a kind of an area by themselves, but all of these together make up the number theory of real numbers. So real numbers are all the numbers on the number line. And there's an infinite number going from negative infinity to positive infinity. And this is what we're using as a well-defined to provide clear illustrations of the kinds of things we're going to be doing. Now you'll need to work with this a little bit and study them. That is the nature of this lesson. Now, some more vocabulary. When we define the number of elements in a set, this is called the cardinal number, or the cardinality of the set. And the symbol for that would be the cardinality, or the cardinal number of set A. Remember, we're using capital letters for the set, and then the letter N to indicate the cardinal number. So let's do some examples. Again, once you are familiar with the background, these are easy. So in letter A, 1, 2, 3, 4, there are 4 elements. In set B, there's just 1 element. Now in set C, they're repeating, which normally they don't list them in their repeating form. So we only count 1, 2, 3, not the repeats. So there's 3, and you would need to know that. Now for letter D, again, with the ellipsis, it might be a little confusing, so you would have to actually list them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be 10. And by definition, an empty set, its cardinality is 0. There are no elements. And if you want to read in more detail, it's right there. All right, in this, So what we're saying here, and they state it very succinctly here, if the cardinal numbers of a set is a particular whole number, and whole numbers, remember, are 0, 1, 2, 3, the counting numbers plus 0, then we say it is a finite set. But you'll find that when you're defining a set, and it's impossible to get a whole number, we call that set an infinite set. And we'll have some experience on that coming up. Let's look at what would be an infinite set. Here you couldn't have a whole number that would define the elements, the number of elements, the cardinality of it. So they're asked here to use the 3 methods that we've started this section with, 3 common methods of set notation. So the word description would be the set of all counting numbers. The listing of it would be counting. We would start with 1, commas, set up our ellipsis, indicating the pattern continues. Now again, this would go on to infinity. This would go on to infinity. Things that are going to go on to infinity cannot be, in a sense, counted. So that would be an infinite set. And then in set builder notation, it's right there. X is such that X is an odd counting number. All right, let's look at another topic now called the equality of sets. Now this is defined by if set A is equal to set B, providing the following two conditions are met. Every element of A is an element of B, and every element of B is an element of A. And we'll see this. So, two sets are equal if they contain exactly the same elements, regardless of order. So here, they're exactly the same. The order's mixed up a little. Now here, when we see repetition does not add new elements. So the ones are repeated, even though you might say, well, there's more ones here. These sets are considered equal. Repetition in a listing does not add new elements. Okay, so they're asking us to determine whether these sets are equal. Well, as you quickly view it, you see this one contains an O, or I should say a 0, and this one doesn't. So these are not equal. Okay? Now, set A, if this is A, is included in set B, but not all of B is included in set A. All right. Okay, looking at example A, we're determining whether or not these two sets are equal. Well, here we're saying this set only contains the counting number 3, and this set is the counting numbers 2, 3, 4, the numbers in between this. So these are not equal. In this case, we have x is a negative whole number. Well, by definition, and this is where you need to be familiar with your sets, whole numbers are 0 and then the positive counting numbers. So there are no negative whole numbers. So this is an empty set there. And then this set, they're saying y is a number that is both rational and irrational. Well, a number is either rational or irrational, not both. So those numbers don't exist. So this is an empty set. So does an empty set equal an empty set? And the answer is yes. In letter C, things are getting a little tricky, and you need to be very careful about what they're saying. So here we have 0, 0, 1, 1, 2, 4, and what are they indicating in this relationship? Well, we look over here, we're saying the ordered pair, in a sense, x, y, x is a natural number less than 3, and y is the square of x. So, first of all, when you think of natural numbers, is 0 a natural number? No. So these do not equal, even though part of that pattern later is true, that 0 is not a natural number. The answer here is no. And you can read more about it here. As we wind up our first topic, notice there are exercises that you would be doing in the old days for homework. I used to assign the odd examples. You'd keep this in your homework log. but now you're going to keep your homework log, but you're getting your examples from your study plan. And we'll do some classwork as well. Okay, this wraps up our first session.